the APQP series from the Supply Chain Management Handbook Awareness Seminar. And in particular, we'll be covering measurement systems analysis today on December 5th, 2019. And my apologies for those of you, but we moved it a couple of days. I had some travel issues and I was not able to attend, and so we had to move it. So again, my apologies for that. Who am I, you may ask? My name is Peter Papadopoulos. I work at Pratt & Whitney as the Senior Fellow in Quality, and in general, I've been in quality for about 25 years, and I think I did my first measurement system analysis about 20 years ago. So it's been a long time. It's one of my passions, the topic of measurement systems analysis. So I hope you guys and gals on the call will appreciate the information today. And along with myself is Sue Parsons. Say hello, Sue.
Hello, everybody.
From IAQG, who's definitely our right-hand person there, making sure that we always have good webinars at SCMH. All right. I already talked a little bit about this. The tips we covered, make sure you have any applications closed that you don't need to prevent any lag in the screen time. We'll be covering measurement systems analysis and then Q&A at the very end. And we will also talk about where and how to access the SCMH. All right. So this APQP and PPAP webinar series, there's been a couple. Well, we did a whole series last year. Again, this is kind of round 2. In particular, we will be covering measurement systems analysis. In general, you can see that the major areas of APQP: design, risk, process flow, control plan, measurement system, process capability control, and PPAP. We'll talk about the schedule at the very end, but January 7th, I believe, is the next webinar covering process capability and control. All right, so what is the relationship with measurement systems analysis to the other major deliverables in the overall APQP process? So if you understand the APQP process as the 5 phases, a lot of overlap in all the phases. But at this point, we have already planned our products. We've done PFMEAs to make sure we understand the risk of the product. But one of the main things when it comes to risk and control is the control plan, as well as process capability, and in particular, if you have safety key characteristics or any other key characteristics. We are in the yellow area, which they're related to all of those. What do I mean by that is that without a robust measurement systems understanding or analysis, all of the information and control plans and process capability and key characteristics may be not as robust, because without understanding our measurement system, are we sure that the features that are listed in the control plans, that we'll be able to tell the good parts from the bad parts, or the pass versus the fails. So it's through an MSA, we start reducing the risk of measurement system error and understanding the measurement system error, so that way we know that we have process control and process capability, and in particular for key characteristics, whether they be inputs or outputs, that we can measure them and we know that they are in control. So again, we are there in the yellow boxes, and we will continue. Hopefully, by the end of this webinar, participants will be able to define what is a measurement systems analysis, outline the process for it. We met a couple years ago. We started working on measurement systems analysis for the SCMH, and the first thing that we did was come up with a really good process flow. So that's going to be one of the major, I think, benefits of this webinar, as well in general what's in the SCMH, is that we talk about the process of it and have the process flows laid out for you, and including gauge selection and variation analysis. We'll talk about the benefits of MSA, where we've seen great strides in quality improvements because of the measurement systems analysis. And we will walk through step-by-step on how to do one MSA, a very simple one. There are actually 5 case studies in the SCMH material covering a broad range of gauges and situations. So when people ask, what is an MSA? Overall, it is a statistical tool. And why is it a statistical tool? Because you're going to use the risk involved, the uncertainty involved, to figure out whether or not the measurement system you're using is acceptable, right? Part of that is going to be accuracy, part of it is going to be precision. And we'll explain those terms a little later. We really truly need to understand in MSA what is the variability or the error. As I mentioned, we talked about in the previous slide, there's a risk associated with your process and your product, and this is another way to quantify that amount of variability, or what you would call the error or risk. Now, if you do an MSA properly, you'll understand if there's training needed, if the procedures are lacking, or if the standards really need to be defined better, right? That's all part of the MSA. Some people think it's all about the calibration only, but truly understanding what is measurement system analysis, you broaden your definition to understand that it's all about everything that could be associated with affecting your measurement. An MSA addresses both precision and repeatability and reproducibility of that precision, as well as accuracy. To truly understand accuracy, you start with calibration. That starts the accuracy question, but as you get into other terms such as bias and linearity, you'll see that it could be accurate in certain regions, but not all regions. So we'll talk about that. Overall, as I mentioned, you're trying to understand the effectiveness of your measurement system, its ability to both measure the inputs as well as outputs. Because not only is it important that you measure the inputs of your measurement of your process, or the outputs of your process, you also should be measuring your inputs of your process. For example, if you are heat treating your parts and you're using a thermocouple to measure the temperature inside, the gradient inside the oven, I mean, are you sure that, how sure are you that the oven temperature is accurate? Also, how sure are you at the readings of the oven temperature if you're relying on the oven temperature to control your heat treat cycle? I mean, these are very important questions, and it's all about understanding what process risk that you may have, in particular the risk of not being able to measure the input or the output. Another great time to use an MSA is if you have a new or modified process. So you're using an equipment that you've always used to measure something, but if you've modified your process, you also want to make sure that the equipment is still capable, the gauge is still capable of measuring features of interest. All right, so to define what is a measurement system. Simply stated, it's a set of elements used in combination to take a measurement. What do I mean by that? As the picture depicts, you have environment, right? The lighting situation, the actual heat or the temperature of the room. You have whether or not it's a loud environment. All these things, the environment in and of itself is part of your measurement system. Why? Because it actually can affect your measurement. The gauge in and of itself and the operator. Those are the three areas typically thought about when discussing what is a measurement system made of. It's really all of the elements, because if any one of those elements and all of those elements can affect your measurement, then they are part of your measurement system analysis, and you should always look to see how much variation each one of those is causing. In this example, you can see if you were going down the side of the road, and in the United States, it's pretty common. The speed limit is about 75 miles per hour in open highway, and a police officer is there with a radar gun and is going to measure your speed. Well, if he measured your speed at 73, you're probably very happy because he can't write you a speeding ticket. But do you truly know what your actual measurement was? And honestly, that's also part of his equipment as well as everything else. In other words, is it cloudy that day? Is it rainy that day? Did he have it on an interesting angle that may have changed the speed reading that he got on his measuring equipment? right? So all of that variation is part of a measurement system analysis to understand what it is that is the true reading that you should be getting. In other words, was my speed actually 73 miles per hour and he got 73 miles per hour, or was my speed limit actually above 75, but because of the measurement error, he clocked me at 73. All right, so that's really the point, is to understand how we get accurate, repeatable, reproducible results every time. And think about the quality implications there, right? You know, someone may have a part that's the same way. They measured 73 on the part, but you don't know if it's truly in tolerance or out of tolerance because there is measurement system variation associated with that. All right. Now, as I mentioned, what could cause that, you know, being above or below 73? And it could be any part of a measurement system analysis. It could be the accuracy. In other words, was that gauge calibrated that day? Was it the resolution? Was it just not fine enough resolution? Maybe it only goes up to 73 or increments of 5 miles per hour, some, you know, decimal point. But you have to understand the resolution. The stability over time, maybe that gauge drifts over time. In other words, it starts changing measurements. The measurement gets lower over time for whatever reason. You know, the diodes wear in the radar gun. And linearity of the instrument. In other words, is it good for all ranges of measurement? And then the last little bit, which is typically more familiar with people, are the repeatability and reproducibility of the measurement, also called the gauge R&R. So all of these things can change your measurement, are part of the uncertainty of the gauge or the error of the gauge that we are going to try to quantify in a measurement systems analysis. Right? Some examples of what may cause variation, right? In instruments, we have micrometers, voltmeters, coordinated measurement systems, and they are all going to be affected by the environment, dust, oil, temperature, vibration, or the operator using it. Is he untrained? Is he unskilled? Right? Is he having a bad day? Right? As we mentioned in the previous one, all three are parts of the measurement system: the actual instrument or the gauge, the environment, or the operator. And all of those add up to give your overall variation that you will see in your actual measurement system. As I mentioned, this is the process flow diagram. There was an SCMH team, as I mentioned 2 years ago, with people from across the globe. It wasn't an American-centric or European-centric. We included anyone who wanted to be on the team. And what we came up with, exploring, you know, our best practices and everything that we do for measurement system analysis, there's probably three major areas when you're talking about measurement system analysis. One is choosing the right gauge. In other words, looking at the gauge, will it perform, is it in the right ballpark to be able to measure what you want to measure? Step two, overall, is, well, understand the actual variation. Now, choosing the gauge, you know, based off of whether it's your gauge supplier's recommendation or what you've always done in the past, is a good start. But when you actually measure the part, you actually have to measure the variation you're seeing in that part, because it should be in the environment that you're using it, as we talked about, that's part of it, the operator that's going to be using it, as well as the gauge. So the variation analysis is the second step. And finally, depending on whether you pass your MSA or fail, you analyze all the information and you may have to take action. In other words, how do you improve that gauge that didn't meet all of the criteria, whether it's linearity, bias, accuracy, or reproducibility and repeatability. So those are the three major steps. We will be covering these in detail, and even when we get to the example, we will go through all of these steps one by one in the simple example. All right, so if we're talking about part one, choosing a gauge, the first thing you have to understand is what is the part feature, the tolerance, what methods do you currently have, what gauges do you currently have, what are trained operators, right, and what, do you have a suitable environment? So first thing you need to understand is, I'm going to get a gauge, I need to make sure I understand what it's going to be used for, where it's going to be used, and who's going to use it. So you take that as the first step and say, okay, here's the information that I have. Then you start looking at, okay, based off of that feature of interest, do I have the resolution that I need to measure that feature? That's the first step, and usually people just say, okay, well, what's my resolution? Typically what they call a 10-point resolution scale. In other words, for a variable, I'll be able to subdivide it into 10 pieces. Then you go into a measurement uncertainty of the gauges. In other words, this goes to the actual published information on the gauge, or possibly even looking at running a study if it's not published to understand what is the uncertainty based off of the tolerance of that feature. We'll talk about that, and there's a ratio that most companies have, but there's multiple ratios depending on also the criticality of the feature. Then you actually take that gauge after you determine it's the right gauge or you believe it passed at least the appropriateness of resolution and uncertainty. You will run an accuracy, linearity, and stability study to make sure that in the application that you're doing that it has the correct accuracy and is not nonlinear over the range of the samples, as well as is it stable over time. Now, if you fail any of those criteria, it says go back, see what you need to do, pick another gauge. Maybe you have a gauge. Maybe you consider only one type of gauge. But either way, if you can't meet all of those criteria, you should be looking at a different gauge, or going back to the manufacturer of the gauge to see, if they reported something versus what you're getting. Maybe there's something that you have to do differently, and if so, go back, repeat your studies with the improved gauge or the new gauge to make sure that you meet the criteria. So if you are able to pass all the criteria, you start into the next group of process steps. All right, now, if you already have a gauge and the application is the same, you probably don't need to run a lot of additional tests. For example, if you know that your accuracy and your suitability and your stability are fine, then you're good. But if you don't have a similar measurement system and there's not something that you already do, you'll probably have to go and try to understand all of the sources of variation, right? Now, by doing that, a lot of people use fishbone diagrams. I mentioned the three major areas: environmental, the gauge itself, and the operator, right? Try to understand those. Once you understand it, you also ask the question, is it software dependent? What we found is that, you think the software can have a stability issue. So you might have to analyze the software just to make sure that you believe that the software is stable. I've had a lot of instances where you've updated some software on a gauge. That would also trigger running an analysis to make sure that the software is stable and that you're getting accurate and repeatable results. But if it's not software dependent, you can go straight to the measurement equipment, understand those sources of variation, and do a gauge R&R if you don't know all of the sources. Again, if you don't have anything similar. But if you do understand all of the sources and you know they're accounted for and you understand them, at a minimum, you should do measurement uncertainty analysis when there are multiple gauges involved. Because what we found is that when you have multiple gauges, they will affect each other's gauge R&R as well as MSA capability. So just keep that in mind. These are the generic steps on how to do that. And lastly, once you conduct your gauge R&R and you pass all your tests, or you run your tests, you look to see if you've passed everything. If you haven't passed everything, you have to take appropriate actions, return to start, because you have to go through the same analysis again. But if you've met all of the elements and the criteria, then you're done. Then you have a robust measurement system. All right. So some key terms that people sometimes confuse, but I want to make sure that we're grounded on, is the terms accuracy and resolution. the difference between the average of measures and a master value. Now what you'll see, what's depicted here, the green arrow being the master value, that is a calibration standard or multiple calibration standards that you may have. That's the number that you should get when you measure it with that gauge. What you end up getting, and I recommend taking more than one sample, is somewhere maybe in the yellow arrow. In other words, if I measure it 7 times as depicted here, I could have 7 slightly different measurements. And so when we talk about accuracy, understanding the variation occurs is fine, but it's the delta between the master value, what you should have gotten, and the average of all those multiple measures that you took. Very rarely would I recommend in a calibration taking a single measure. You usually take more than one measure, and depending on the resolution, that's where you'll see that variation within those measures. You take the average of those, and that's the delta between the two. All right, and so that is what they call accuracy and or bias. Now, resolution, on the other hand, really is the number of discernible digits on an instrument or a gauge that you're reading. For example, if you were to measure the top of this screw, a ruler may give you 0.28 inches because it's only accurate to 2 decimal places. A caliper may give you 3 decimal places, and a micrometer may give you 4 decimal places. Now, over the 25 years, I've just learned that, you know, we like what we like and we use what we use, and, you know, those are the kind of guidelines that people like. Hey, I always use a ruler for this, but when we actually start looking at measurement system analysis, we have to make sure that the resolution is there, the accuracy is there, the stability is there, so that we can have a robust measurement system. Just keep in mind, you know, resolution, and we'll talk about how that fits in the example of the gauge R&R that we're going to do a little bit later. Furthermore, stability, as I mentioned, it's kind of drifting over time. Usually it's the same part is measured, whether it's, you know, over multiple days, over years, just to make sure that you are consistently getting the same result and it's not drifting. And in this case, it's like a variable bias. In other words, it may be right on in the beginning, the exact calibrated number you're supposed to get, but maybe if you measure it a day later, you're going to get a little bit of drift, and it's going to be, the reading is going to be above what you should have gotten. And over time, that number is changing, has a bigger and bigger difference. All right. Linearity, if you've ever heard this term, and this is what I was talking about, that you should be good over the full range, or you need to be accurate over the full range of parts that you're going to be measuring. And sometimes, as we use gauges, especially at the edge of their limits, for example, if you have a 0 to 1 mic, micrometer, you don't want to measure parts that are 0.999 inches, as well as some that are super, you know, close to 0. Because the reason is that all gauges have variability, and it's usually towards the ends of those, either the bottom end or the top end of their resolution, that they actually start breaking down and having a shift or a bias. Right? Actually, when you talk to gauge manufacturers, the ideal location for measuring the parts are in the center of their range. That's the most accurate part, because the accuracy in the middle is going to be what controls on both sides. So they'll center the accuracy in the middle, so that way there's a little bit drift on the high and the low. So most gauge manufacturers will tell you that the measurement should be in the middle of the gauge you're trying to use, not towards the top and bottom ends. But again, make sure you check it. You can see in this case where if this was in the gauge, you have the reference known values, multiple values that you checked. And when you actually use the gauge to measure it, you can see that the scatter was getting greater towards the top end of the range of parts that you reference values that you were measuring. And again, these are the types of studies that you would run in a measurement system analysis to understand if the gauge that you're using is suitable. All right, so as we talk about gauge selection, one of the terms that you'll hear a lot is uncertainty of a gauge, right? Measurement uncertainty is more than just accuracy. It's statistical analysis of the whole system and all influencing factors, all right? Total uncertainty of an instrument is calculated by considering all individual contributing factors that may affect the measurement result, including but not limited to the operator and the environment, right? So again, as I mentioned in the beginning, it's a risk assessment is our uncertainty analysis. In other words, how uncertain are we that we got, an example of 73 on our speed, right? That could be, our true value could be above that or below that. By measuring the uncertainty and conducting these studies, we're trying to understand if the measurement is appropriate and accurate enough and precise enough to give us a quality result. Now keep in mind, if you have multiple gauges that you're using, maybe one gauge to set up the true position, another one to measure the height. When you talk about the overall measurement, both of those are part of your uncertainty of the gauge. All right, now, when we talk about uncertainty, there's actually a standard for measuring uncertainty as it's given in ANSI 7540.3 or ISO 17025. There are actual studies that can be done to measure the uncertainty. And typically when you hear people talk about uncertainty or uncertainty ratios, they are referring to the ANSI standard or the ISO standard for that. So keep that in mind. So if someone just says uncertainty or talks about uncertainty ratios, they are referring to the ANSI standards or the ISO standard, right? Now, accuracy is part of that uncertainty, right, as we talk about calibration, so make sure that you're always calibrated. Also look at all the other factors as well as we talk about linear stability and bias across the whole range. Now, here is that spec I was talking about, the test uncertainty or the ratio I was talking about. Now, when you're calculating ratios, it's a pretty simple thing. What you do is determine the part feature accuracy. That's typically published, or you can do the ISO standard to figure out the uncertainty as well. But you need those two numbers. And once you determine the part feature accuracy, in other words, the tolerance that you are going to be using versus the gauge system uncertainty, that ratio. So in this case, it's 0.01 is the plus minus accuracy needed, or the tolerance. The gauge system uncertainty, whether it was done through the ANSI standard or a lot of times it's published by the gauge manufacturer, you divide those two and it's a 4-to-1 ratio. It's 0.01 over 0.0025. So most companies require a minimum of 4-to-1 ratio. Again, this is not a resolution. This is a test for uncertainty or ratio, or an uncertainty ratio, and that's how you calculate that. Now, is that the only number to use is a 4-to-1? That's typically the minimum, but a lot of companies, if they're dealing with a critical or a safety feature, will have a 10-to-1 accuracy requirement. In other words, their gauge uncertainty has to be 1/10 of the tolerance. All right, so keep in mind or make sure that you understand what your customer is looking for your uncertainty ratio there. Now, besides, again, the uncertainty ratios, we should always be looking at the overall variation. If we know that the part and the process has some variation and the measurement system variation, the actual observed variation is going to contain both. It's very hard to separate the two out. You have to do studies, which we'll talk about, how to understand what the measurement system variation is. But really, when you're thinking about it, when you measure something, you may or may not be getting the true value or the actual value because the operator, environment, and the gauge itself has variation. And so those three together with the actual part measurement, right, will give you a plus or minus some number. And this picture depicts that variation is what you're actually seeing. Now, keep in mind that if you're talking about inputs, speeds and feeds, or even outputs, diameters, lengths, true position, you'll never really know the real number, so to speak, because there's always going to be variation in the measurement system. And what we're trying to do is understand that, quantify that measurement system variation to say that it's negligible compared to whether it's our tolerance or our process variation. Once we say that it's negligent to that, in other words, it's a small amount of that error, then we'll accept that risk, because once we know that we're not getting the actual number, we're actually getting a variant of that number or variation of that number because of the measurement system variation, then we say the risk is low enough that I'm going to accept that risk and that my measurement system is good. So to give you a pictorial about what that risk looks like, think about it like this. If I was going to measure an operator doing the same part over and over and over again, right, that's like showing you the upper left picture where if he is very repeatable, you would have a tight grouping. Again, whether or not it meets the master value or the calibration value, that's a different question. Answered during a calibration and stability. You can even do that by operator if you're afraid that he has some type of bias. But when it comes to actual repeatability or what they call precision, that's literally just looking at all the values he had for that same measure, and if they're tightly grouped, then we say it's precise and it's repeatable. If, though, the next picture just to the right of that, you can see if that operator is getting a different number every time and it's all over the part. And by the way, the average of his parts looks like it's in the center of the true value or the master value, but he has a precision issue where, you know, he gets a different number every time he measures the part, and it's scattered throughout a lot of different measures. So overall, though, precision for repeatability is the same part by the same person using the same instrument multiple times. Reproducibility, on the other hand, is having multiple operators measure the same part, and it should be multiple times as well. Excuse me. And in this example, you can see that on the left side, the inspector A versus inspector B versus inspector C, relatively speaking, they're in the same quadrant of the compared to the master value. So they're pretty reproducible. In other words, they're getting close to the same number. Again, it's irregardless of what the master value should have been. It's just saying that they're reproducible. While the bottom right picture, you can see that the inspectors are all over the place compared to each other. And again, maybe their average value is the master value, but it doesn't matter. They each have a grouping that's tight, so they each in and of itself is precise, but when you compare it across all of the inspectors, we have a reproducibility issue. All right, so that kind of explains some of the components of variation. Typically, they're called the R&R, the repeatability and reproducibility. So now, why does that matter? Now, we know that every gauge will be different. If you're driving along in your car and the police again pulls out the radar, he gets 100, you get 80, 81, who's right? And the answer is, I don't know. Hopefully you're right. But you don't know if his gauge has a calibration error or if it has a repeatability error or if your gauge has a bias in some way and it's reading low, right? So all of these things taken into account, it's really important that we understand how repeatable and reproducible we are. In this case, assuming that the cop always gets, or the police always gets 100 every time you pass by, and yours always says 81. You both can have precise numbers. In other words, get the same number every time, but doesn't mean that they're accurate. In other words, I don't know what the true number is. All right. Now, we do an MSA, and we've talked about the elements of the MSA, you know, accuracy and precision and repeatability, reproducibility, bias, linearity, stability. But we always have to look at this saying, hey, that's could be a very high risk for me to say the part was good, or if the part is bad, trusting my measurement system, not knowing if it's truly capable of giving me an accurate, repeatable result. So that's why you do it. You want to make sure that you understand the sources of variations, you can quantify it. You want to make sure that the right measurement system is being used. You really are warranting the quality of the measurement data, right? And you're going to reduce the false passes or the false fails, both of which will improve efficiency and eliminate potential of nonconformances, making it to the customer. So again, MSAs will help you quantify the risk associated with that, so you can make sure that you can warrant the quality of the parts being produced. All right. And as we all know, measurement is the last line of defense between your product and your customer, right? So how do you know if you are correctly approved your product? Well, if you determine the variation in the measurement system as well as the accuracy, you'll know that. How was the variation in your measurement system determined? Well, you did an MSA. If you don't think an MSA is important, then why should you measure or test your product at all? It's true. If you're okay with, you know, saying that it's close enough, I mean, maybe that's okay. Typically in the aerospace, it's not okay because we have such high tolerances and such high precision, and the safety of our parts is much more important than a lot of other industries. That MSA is really important to make sure that we understand the risk associated with a measurement system. I talked about it in the agenda, but there are a lot of benefits. Improving product quality overall. And what does that look like? Well, I've been involved where I've done an MSA study, and it really helped reduce production costs. How was that possible? Well, the actual production costs were high because we were scrapping a lot of parts. When I actually did a gauge R&R, I found out that people were throwing away parts that they shouldn't have been. Now, that's called consumer bias. In other words, you want to make sure that the consumer only gets the best parts, which is good, but we also know that there's a tolerance on parts. Engineering gives us that tolerance, and so as long as we're within that tolerance, then we know the part should be good. So those will help us improve yield and scrap just by doing an MSA. One other thing that people don't realize is that without an accurate MSA, you really can't do statistical process control. Because if statistical process control looks for common cause variation versus special cause variation. If your variation is coming from your measurement system, then how do you know if it's common or special cause? In other words, you may never detect a special cause, may make it to your customer just because the variation is being masked by the measurement system. All right. In general, as we talked about, that producer and consumer risk are really important, right? To make sure that we have parts, like good parts to make to the customer, and we're not throwing away any good parts. Right. Now, one last thing I would always say too is, I know we're quality professionals, we want to go out to the umpteenth decimal place sometimes, but we also have to think about an MSA as an opportunity to try out other methods. Maybe there is a more economical method of measuring something, but everyone wants to measure it on CMM because that's the most accurate, but it takes too long, they've set it up. Maybe you have bottlenecks in your CMM. So if you have a measurement system that you want to propose and your company could save some money, if you went through an MSA and showed that the risk was extremely low by using this new technique, it's another great way I've used in the past to able to save money for companies I've worked with. All right. Now, when it comes to measurement data types, in general, you have variable data, which are a continuous scale, and that scale can be divided into smaller increments, such as time, temperature, weight, length, torques, right? And typical gauges, CMM, calipers, micrometers, measurements from structured light, torque wrenches, and I'm talking about the ones with torque readings as opposed to the ones that just you set the torque setting. And then there's attribute data. Anything that's classified as pass or fail, or could be a count, such as ranks and orders, right? In other words, visual inspections are pass, fails, and no-go, and good and bad, number of defects. But what if you had a spec that allowed you 3 scratches on a part? Well, you know, is everyone seeing the same scratch as a scratch, right? So that's using visual inspection and the number of defects, right? You can't divide the number of scratches into decimal points, so it's still the number of defects. And so that's how you would use the attribute, or when you would use an attribute MSA. But it doesn't matter if you have variable data or attribute data, visual inspections, whatever it is, all measurement types require an MSA. If you truly want to understand the risk associated with, you know, consumer or producer risk, you have to do an MSA for repeatability and reproducibility, as well as accuracy and linearity and bias. In general, MSAs should be conducted. Every time you have a product escape, you want to make sure that, you know, why did your measurement system, if it was in place, miss that? You know, or was it a issue with its uncertainty or a risk there, or was it something else? If you want to put a new test solution in place, as I mentioned, a new gauge system. How about if you have a new product introduction, new product that you've never measured before? How about if there was a significant design change and a feature is bigger or smaller or new that you don't know how to measure? How about if you're just starting to see shifts in your SPC? It could be a gauge shift and not an actual process shift. And in general, if you have a key characteristic, most aerospace companies require MSAs on the measuring equipment for key characteristics, especially if they're safety-related key characteristics. When you do an MSA, you should always have the personnel that's going to be using the gauges as part of your MSA. If you have an ops program, or even if you don't, the production personnel are setting up equipment when they're taking measurements as they're setting up equipment. I mean, understanding the gauge and their measurement error is going to be critical, because he may be setting up the equipment incorrectly because, you know, his gauge capability is not there. Typically, quality engineers are involved with, you know, running the MSAs and getting all the people. They also may be measuring parts. So again, they should be included in the MSA. The inspectors, obviously, all the people actually making final inspections and inspections in general and are using gauges, as well as the manufacturing engineers. I mean, they should understand the complexity of the designs as well as the manufacturing to understand which equipment and gauges are going to be used during the manufacturing phase. So they should be part of understanding the MSA and its results. So when you're going to do an MSA, make sure you have the parts that are going to be measured, the time, manpower, equipment, the MSA plan, and training. If you do an MSA with untrained operators, with not the equipment that's supposed to be used, you're doing it on some parts that are similar to but not exactly, all of those can lead to false results. So make sure that you have the actual parts, the time, the manpower, equipment, and the training to make sure that that's indicative of the actual process you will use, whether it's production or whatever environment the actual gauge will be used in. What you'll get out of the MSA is collect a lot of data. You'll be able to analyze and interpret the data. You'll be able to look at the potentials of new test solutions or processes. And you know what? If you don't pass, you probably have an action plan. You should look at the results. You have to analyze them. I personally use Minitab, but there are a lot of other, even Excel spreadsheets people have created over the years. But analyze those results. And again, if you fail, make sure that you have a resolution of that. and if you have to have a plan, make sure you implement any of your solutions, and then redo your MSA as needed, or which parts of the MSA you had plans against. But I would also say anytime you add a new operator or if the process changes, make sure you monitor and make sure that the MSA is still valid, or run sections of the MSA that you need to, whether it's an R&R study or calibration as needed and required stability studies over time, just to make sure that the process is still robust. All right, so now we will start the example. Hopefully you guys like this example. In the case study, you have a simple cylinder with two basic requirements. It needs to be 1 inch tall with a 0.1 inch tolerance, and it needs to have a diameter of a 1/2 inch with a 5/1000th of an inch tolerance. Okay, so this is it. Maybe it's a precision pin that you need for a part. Who knows what it's used for? But those are the tolerances that are needed. So we will start walking through that step-by-step procedure that we talked about. Step 1, as we mentioned, do we know the part? Do we know the feature? Know the tolerances? Do we know which gauges that we have? Do we know which operators are trained on those gauges? And do we know how and where we're going to measure this part? So once that's done, all right, we start gathering that information. We said, you know what? We are going to use from our gauge inventory. It could be a CMM, it could be a caliper, it could be a micrometer, it could be a steel rule. All right, so in general, we talk about resolution being 10:1, we mentioned on the previous slide. So we have to make sure that if we're going to measure, and the tolerance is 0.01, gauge needs to be at least 0.001, right? In the case of the 5 thou tolerance, I double that because the actual total tolerance is 0.01, so it's 10 thou total tolerance. So whatever gauge I use the diameter has to be able to report at a minimum to be 1 thou or 10:1. All right, so for my diameter, I need a gauge that has at least a 0.001 resolution. All right. Now, keeping that in mind, I also talk about the criteria that we needed, the 4:1 ratio. So I look at this and I say, okay, well, the tolerance for my part diameter is plus or minus 0.005. All right, my gauge needs to have an accuracy that's 4 times that. Remember that accuracy we talked about before in the previous example. So I just divide that number. So the accuracy and the tolerance of that accuracy needs to be 0.00 or 125 10,000. Right? And that's typically posted by the gauge manufacturer of what their uncertainty is. And so using the 4:1 ratio, I have to have equipment that has a tolerance of 0.00125. Now, for linearity, it's recommended that the gauge be taken in the middle of the range. In this case, we know that the height is, the diameter is a 1/2 inch. So I'm going to use, recommending using a 0:1 mic, which has the uncertainty that I need, as well as the 10:1 ratio. And that's what was chosen in this case. Just use the mic. It had everything I needed, and it met it. Could I put it on a CMM? I'm sure I could. But for this simple pin, I wouldn't use the horsepower on that. All right, so here we are. We're going to talk about that pin. We know that there are sources of variation. In other words, man, that's a pretty small part. So someone's going to have to hold it in their hand, or how I'm going to do that. It's going to be lots of sources of variation. I could do a fishbone diagram, figuring that out, making sure I look at all those sources of variation. And even before I conduct the study, maybe there's something I want to do, make that part of the standard work for that part. You know, maybe it's, putting in some type of fixture, or what I'm going to do to hold it, or maybe, make sure that people hold it with their left, or tell them hold it with their right hand, whatever it is. So we look at the sources of variation. Then once we determine those sources of variation, figure out what we want to do to start controlling those sources of variation, you take 10 parts recommended, but you can do it with a minimum of 5. And hopefully they span the normal process variation. In other words, if you take 5 parts in a row, it may not span the process variation that you actually have. So hopefully you can gather parts over many different times, whether it's over many different months, if possible, or at least over a couple of weeks or a couple of shifts. Take all of the operators that are going to be actually measuring and using that gauge to measure that part. A minimum of 2. If you only have 1 operator that's going to do it, you could do it with 1 operator. I recommend doing it with someone who would be checking or who's going to be filling in for them, or maybe a QE that will have to help every now and then, you know, when there's the issue on the shop floor. But anyone who's going to be responsible for measuring that diameter should be part of the MSA, and in particular the gauge R&R. And again, make sure that everyone's trained as well. I mean, you don't want to have someone who's not trained on how to measure, because most likely you'll actually fail. And don't forget, gauge R&Rs are actually supposed to be performed in the location where it's typically going to be done. In other words, if this is a measurement that's done on the shop floor, then do the gauge R&R on the shop floor. All right, take the measurements. But before you take the measurements, make sure that everything, you know, that the gauge was calibrated and is in proper operation. Make sure that, you know, that it's well lubed if it needs lubed, or it's moving freely and it's not getting stuck. So make sure it operates properly. Typically, people have templates. If you're using a software such as Minitab, you can create a template quickly in there. But make sure that you have enough for all of the operators, the number of measurements, and the number of recordings for each part, right? So in this case, it says 2, 10, 2. So this is 2 operators, 10 parts, doing 2 measurements each for a total of 40 measurements. You know, 2 for each part for each operator. And you record all those. And again, if you have 3 operators and 5 parts and 2 measures, but you have to have at least 2 operators, 5 parts, and 2 measures. That's the minimum. But again, you can always include more. Conduct the R&R, it says, and get the results. In this example, we'll show you the results here. As I mentioned, I tend to use Minitab. It's a pretty good software package. And you can see here we had, I believe it was 2 operators, Gustav and Jay, and 10 samples, and they measured each one twice. This was for the diameter. And you'll see 2 numbers that typically people talk about when they talk about gauge R&Rs, percent study variation and percent tolerance. We'll start with percent tolerance, which is the more common requirement by customers. This is a ratio of the uncertainty in your measurement system divided by your tolerance for that part. In other words, in this part, we had a plus minus 5 thou for a total of 10 thou tolerance. And how you actually derive that number, if you read across, you actually take the standard deviation of your gauge, multiply it times 6, and then you divide your total tolerance by that number. Because 6 is used, it's plus minus 3 standard deviation, so that's 99 plus % of the time. In other words, that's the range of the error that you'll see. And so because it's 6 times that and you divide by tolerance, you get a 23% percent tolerance. There is no hard and fast rule. Some people use 30% as a good rule of thumb. Some people say 20% if it's a key characteristics or a safety item. You'll have to ask your customer or whatever standard. You can read a lot of books on this too. Not a lot of them will say a number. That is your risk that you're assuming. And if that risk is good enough for you and your customer, 23%, then that's fine. If it's not, we'll talk a little bit later what you need to do. Now, the other number I actually circled here is the percent study variation at 24%. That is actually taking the 6 times the standard deviation and dividing it by the variation amongst all of the parts. So as you subtract the high and the low, right? So that's slightly different than tolerance, because so the study variation is all about having parts that represent your actual process, because if they don't represent the process, they're all continuous parts, and they all have the same number, your percent study variation will be very high. In other words, there'll be more variation in your gauge than in your parts. Again, that's the ratio of the gauge variation divided by your part variation. Now, why is that important? And this is what we talked about, is that's how you know your SBC is working well. In other words, if all of your variation is coming from your parts, and then it's a good sign that SBC will be indicative of special cause. But if all of your variation is coming from your gauge will mask any variation, because it'll be more variation in your gauge than in the parts. Now, another interesting part that I like to explain with Minitab is as you go down that column, I'll go back to the percent tolerance, you'll see that reproducibility makes up 23% of the 23.17%. So you'll know that the operator variation is causing more variation than anything else. So that's important, because if 23% was too much, or if you wanted to have a better gauge because that was too much risk for you, this is going to help you narrow in that says that the operator's reproducibility, in other words, between operators, there is a bias. In other words, one operator tends to have higher results than the other operator. All right, so as we look at this, what we'll see is that if I wanted to make changes, I have to figure out, I can look at Jay's versus Gustav's results, and it appears that just by looking at the numbers, that one tends to be higher than the other. So we have a little bit of a bias there between operators. Who knows? It could be the technique that they're holding the part. It could just be the way that they look at it. Who knows? But that's some of the stuff that you can get from the gauge R&R study. All right, so in this case, we want to make it better. So we're going to talk about training, maybe better documented methods, improving skills, improving ergonomics. Those are typical action plans that I see in industry and people doing gauge R&Rs. If you want to improve it, you go make those changes, and then you can remeasure it. Again, you should be measuring all the people, again, not just the one that you thought was too high or too low, because you want to get a true representation. Because if you make changes, you want to make sure everyone is doing it the new way, because someone may have a problem with the new way that someone else did not previously. All right. In summary, a measurement system is more than just a measurement instrument. It's a set of elements used in combination to take the measurement. Right? Again, you have the operator, you have the environment, and the gauge, as well as maybe multiple gauges as well. Measurement system analysis takes all of those into account, analyzing the variation, quantifying the risk, and it's up to you and your customer to determine if that risk is too high or too low, or too high, not too low. When a measurement system is conducted appropriately, it will help improve the overall quality. As I mentioned, you'll make sure that you're not throwing away good parts or having problems with bad parts. Now, as I mentioned again, there is lots of information on the SCMH. We just covered one case study. There are 5 case studies, so there's lots of good stuff in there. It's always good to go back. We included different types of equipment, different types of gauge R&Rs that you could conduct. But we went through all of the steps of how to conduct an MSA in those case files. In general, I recommend everyone have working knowledge of APQP and the AS9145 standard. Again, measurement system is a big part of that, or at least part of understanding our process capability and control to truly understand it. One of my favorite books, I read MSA 2 for the first time, and that was probably 1994, I think. Now they're up to the 4th edition. Not many major changes, just some minor edits. But it's a really good book. It's about 200 pages, and it has a lot of formulas in there, a lot of theory, a lot of risk assessments and discussions within that book. And again, point you back to Section 311 of the Measurement System Analysis in the SCMH, Section 7.2 of APQP, and overall AS 13003 spec talks a lot about as well as the how-tos of performing measurement systems analysis. And those are the requirements for the aero engine supply chain. But it's a very good standard written by one of my colleagues here at Pratt & Whitney. Just keep in mind that aerospace section SCMH APQP section 7.2 has a lot of information there. Again, if you go there, it's got a lot of checklists by phases, a lot of tools and templates for process flow diagrams, P from E as D from N as control plans, maturity assessment, something that just got launched, as well as those tools got updated, and overall the APQP manual that's in there. All right, so again, we got some more webinar series coming up. In the next one on process capability, we'll talk as well about process flows, diagrams, and control plans. And on January 7th is that process capability one. So hopefully you've enjoyed the webinar series. I know I have. Again, these are the ones that I've already completed for the second time again this year, and the ones coming up. I will be on the one on January 7th as well. We also have a SurveyMonkey I mentioned in the very beginning. If there's room for improvement, and we are quality professionals, we always love good suggestions on how to improve, please use this link, or you can go to the SCMH to find this link. They are all anonymous, and please refer to this webinar, MSA, if it's specific to this, or anything else. And again, this is how to get to the SCMH and the handbook. That's all I have for you today.
Great job, Peter. Thank you. You're going to have a lot more coming because you're going to answer some questions that I'm about to read to you, so everybody should stand by. Don't drop off yet. You're about to get all your questions answered, I think. But this is Susan Parsons. I work for the IAQG. I support the PSCI team and, of course, the SCMH. I'll be answering a few questions that were general, one of them being about the locations of the webinar, the recording, and things like that. So we have the webinar up on the screen there. There's a tab. You'll see this presentation along with some recordings, Q&A. We'll update the Q&A based on the questions that came in today, of course. And the recording, which might take a couple days so we can review it, but it sounds great so far. And then I can start the questions now. So the first one up, and Peter, some of the questions might have, of course, been answered in more detail as they went along. So I'm asking these in order that they came in.
Yep.
And if you feel that you want to add something to them, great. If not, and you've already answered it within the presentation, that's fine too.
Okay.
So the first. Okay, ready?
I'm good.
All right. Is a standard gauge R&R usable for CMM, or does the evaluation of the CMM require a special gauge R&R? If so, can you recommend an Excel file that does this well?
So, it doesn't require a special one. I've done CMM R&Rs, many of them, as a matter of fact. People sometimes try to say that CMM is so accurate it doesn't need an R&R, but again, an R&R would tell you compared to your tolerance. So you have your ratio, which is typically 10:1 on a CMM. That's a good sign. But when you're actually measuring the part, as well as I found the technique and how they go into the part, require a gauge R&R, but it's nothing special. I will see if I have a form in general to post on gauge R&R. We have one here at Pratt. I'll just see if I can release it, and I'll ask Sue to post that somewhere in the SCMH. But it's just a standard gauge R&R is fine. There is no special one for CMM.
Yeah, if there's interest in templates and things like that that go along with APQP in any part, or specifically with MSA, it's good to know, and we can add that to that 7.2 section. You see on the screen, tab 7, and we can put that there. Just a quick note too, that's also at the bottom, the last item in 7.2, I think it's 7.216, contains the survey too. So you can put your references and answer that for us, helping us out, but also ask your questions in that survey as well.
All right. Question?
Yeah. And, and just another quick note, a lot of people are sending their questions through the chat. I'm not able to read the chat questions. I'll be reading them from the Q&A box. So please take them into the Q&A box. And there's quite a few, so we'll see what we can get through. This one I think you answered. It's asked a couple times, but just to clarify, when you talk software, are you including embedded software?
Yeah, that's specifically what we're talking about. And I haven't experienced this personally, but in our team meetings, you know, when we have embedded software and the software gets an update, that is a great, well, it's an opportunity to double check to make sure that that software update doesn't change your repeatability or your accuracy or your bias or your linearity. And that's what we've seen. In particular, there was some embedded software for a to measure resistivity, and that changed the results that they were getting. And so, yes, embedded software as well. That has opportunities for R&R capabilities or I'm sorry, MSA error issues as well. So yes, embedded software included in that, especially when updating.
I believe you had an example of this, but and if I read this right, how can I separate gauge R&R for persons and for devices?
Oh, no. So unfortunately, all we can do is separate it by repeatability and reproducibility. The gauge is part of that system, and so those are the only two elements we can separate it out to. The only thing I've ever seen is doing a whole bunch of samples and not doing multiple operators, and then make some type of assumption that, you know, that it's all from the variation. But it's hard because even if you're just saying it's one operator, one part, multiple times, and just call that your pure error, it's not really just gauge error. So I have not seen anything to take out just gauge error, because no matter what happens, there is someone that's part of that gauge or measurement. So yeah, so you can go to pure repeatability error. Some people like to say that that's just gauge error or tool error, but it's not, because you've got embedded in there the person as well and the environment, some other things. So unfortunately, the closest you get to that would be the repeatability. And even that is masking because it's got the operator.
Thank you. Is there a suggested golden rule to choose resolution of the gauge in comparison to the tolerance we have to measure?
Yeah, for resolution, it's 10:1. But keep in mind, that's not the accuracy ratio. Again, those are two separate numbers. Sometimes people confuse. So in other words, but the golden rule is that based off of your tolerance, you need to, at a minimum, be able to split your tolerance into 10 parts. So if you have a 1 thou tolerance, then you have, or a 10 thou tolerance, you have to be measured within the 1 thou. And that's just a starting point. When you actually start measuring it and you start seeing that you may have resolution issues later, but the 10:1 is the rule. And then when you actually, if you ever measure uncertainty as far as the the ANSI standard, then that's the 4:1 ratio or 10:1. But again, that's your uncertainty variation.
I believe you expanded on this already, but in case there's something you would like to add, how does MSA differ from SPC, or is SPC a component of the MSA system?
Yeah, so SPC, statistical process control, is plotting the result of a measurement. Now, what an MSA does, it gives you confidence in that measurement. So SPC is, graphing and plotting your measurements, while MSA doesn't graph and plot the measurements. They make sure that the measurements that you're actually measuring are accurate, and they don't have bias, and they don't have repeatability or reproducibility variation. or a small amount of risk within that. So yes, so two different things. SPC is measuring the part over time and plotting it, looking for special cause and common cause, while an MSA is measuring the actual measurement system to make sure that it gives you robust results that you can SPC it.
Next question is asking which standard is IAQG following? For example, the AIAG MSA, the VDA5, ISO 22514-7, or is IAQG planning to set up its own standard?
The only standard right now that's been published is AS 13003 in the aerospace industry. So I can't talk about the whole industry, but I know at Pratt, that's the one we've been following. Now, there's limited parts of that if you're one of our suppliers, because there's some parts of that standard that we don't necessarily ascribe to, so there's limitations on that standard, but that's the only standard that we use. By the way, the other, if I'm not mistaken, we say MSA, the AIG, those are actually not standards. They're actually reference material, very good reference material, by the way. So slightly different concept versus a standard. In other words, the reference material has how to calculate, what's a good level of risk versus a bad level of risk. But the AS 13003 for the aerospace is the only actual standard that's out there. Again, we ascribe to that, but I can't speak for all of the airframers and OEM.
Do you need to do an MSA even though your instruments are calibrated?
Yes. So the calibration part gets you through the first loop. So let me go back to. I will go back to this one. And this is the reason why, as we talked about, right, the process flow, the calibration, uncertainty, and understanding it, that gets you just, is it an appropriate gauge? But the second area is to look at the variation, because don't forget, what makes up a system is all of your components, right? It's not just the gauge being calibrated is the first part. The environment and the operator, by the way, you add the part, whether it's the how I hold the part itself, all of those add components to variation. So what we're trying to do is understand the variation as well as the calibration. So the simple answer is you need to do both. The calibration gets you in the ballpark that it's a good measurement device to start with, but when you actually quantify the variation, you may be figuring out that you're throwing away good parts or sending bad parts to your customer because there's more variation in the system than just calibration.
Okay. This one's a comment but leads to a question. The
Okay.
MSA just identifies variation and helps to allocate it to variation source. The actual mitigation potentially eliminates variation, right?
Correct.
i.e., for example, DOE, procurement of better equipment process redesign.
Yeah, exactly. So I'm going to go back to should have just stayed there. But yes, if you fail an MSA, and again, you could start by failing the calibration, right? Or it could be any of the elements. You may have an action plan, but you're right. Once you quantify where you're failing, is it that you're biased? It could be part of the scale that you're biased on. Could it be this certain operator? Those will give you actions and help you to improve your gauge. So yeah, that's why you run the MSA, is to figure out where there's a high amount of risk in your gauge, whether it's operator variation, whether it's part-to-part variation versus gauge, methodology, or even the selection, resolution, and uncertainty ratios. Take all those into account to help you choose a better gauge, or to your point, even just actions to make it better. But that's a great comment. Thank you.
And what is the difference and or similarities between MSA and ISO 10012 meteorological confirmation?
So I am not familiar with 10,012. Okay. So I'm going to have to do some research on that one, because that's a standard that I'm not familiar with.
right, we can look into that. Can the value from SPC taken to be added in an MSA?
I'm sorry, could you repeat that?
Can the values from SPC taken to be added in an MSA?
So the short answer would be yes. So the way that, an MSA is set up, you have to have the measurements from multiple operators, multiple parts, multiple times. So my only, caveat to that would be is if I'm taking data from SPC, that I would have to be able to trace that data back to the operator and the part and be able to have another operator measure the same part multiple times, as well as the first operator has to measure the part multiple times. So if all the conditions are met, in other words, the same part measured multiple times by multiple people, then you can use that data. Again, I'm assuming each data point on your SPC is a different part, so that's how you could possibly use it. I personally have not done it that way because I would like to make sure that, because if I measured multiple parts over multiple days, I'm not keeping the environment constant for those parts. And so I'm going to be introducing a lot more variation. So just the other part is if you fail, it could be the fact that you're measuring it over different days and different times, which is good information. You just won't be able to separate that out because it'll be confounded with everything else.
How do you do an MSA on an oven that has been calibrated and a temperature uniformity survey done on it?
All right, so I used to do this. Basically, and I worked in a paint factory years ago, and I would run multiple thermocouples in there. And so I would actually assume my separate thermocouples were my different operators. So it was kind of a modified gauge R&R, I would call it. And I would do it at multiple days and multiple times and do multiple samples. And so there's different ways you can assume the multiple operator, or you can even have two people put in the thermocouple in the oven. And there's a destructive test version of gauge R&R as well. So if you assume that you can't have the same sample, but you have the same temperature setting is your sample, and you do the range of temperatures that you're usually on the thing. Again, you're trying to pick up and understand so you can do the calibration as well as understanding if you're getting variation in your measurements. And that's exactly what I do. Once a month, I would have to do my oven R&R to make sure that I understood all the temperature variation that was caused by the oven itself as well as the gauges. So just multiple gauges is how I used to do it, and I would consider those multiple operators.
And I'm going to read this because it's a comment just for an improvement on the presentation, a suggestion, and then we'll go on to the next one. I just want to acknowledge it, and we'll review it later. But it's a comment. I would include new measurement equipment introduction in the line MSA should be conducted when.
Yeah, perfect.
And other than that, they said, great presentation, thanks.
Well,
so we will take that into that. Okay,
absolutely.
Next question. All right, next question. How would you perform a gauge R&R with a torque wrench, especially when with an analog one? I mean, you are not directly measuring with it. You just get an info that the set values have been reached.
Agreed. I think I kind of alluded to that. For click torque wrenches, you can't do a gauge R&R other than if people can hear the click or not. So it's like an attribute R&R. What I would suggest is that I was really talking about the digital torque, as well as a lot of people are using the new torque guns and stuff. And so they'll actually, torque and untorque those with different operators to see if they're getting the same results. Again, that goes back to this kind of modified destructive testing because the sample obviously changes every time you torque and untorque something. But yes, for click torque wrenches, you are 100% correct. Attribute at best to see if everyone can hear the click or not. But other than that, no, for click torque wrenches, no. Typically, I don't do them there. It's more on the variable torque wrenches.
And how do you do an MSA on a software-driven CMM?
And what I've done, like I said, I've done many of these. I literally will have them set up 5 parts with 2 operators multiple times, and I have to take them off the CMM and put it back on. That's part of the process of a CMM, is actually being able to load it onto a fixture onto the CMM, and that's really what you're trying to get. Remember, it's the environment, it's the operator, and it's the gauge itself. So in the instance where I've seen someone say, well, I just put it on once and I measured it a whole bunch of times, that's where you're looking at the one operator variation. In other words, the operator set it up, the one person who did it, that's great. And some people call that the pure variation because it's, you know, taking out all the other elements. But a CMM, gauge R&R, you actually unload the part from the 5 parts, put them on and unload them. The second operator does the same thing, and each operator does that twice. Again, it's very time consuming, I understand, but if you truly want to understand the variation, because remember, someone has to load that part onto the CMM, someone has to take the CMM, you know, I don't know how you start it, whether it's a fixed fixture, a starting point, that's all part of the methodology, and everyone who's running a CMM, they do it slightly different or may get a different result, and that's what you're trying to prove out. Yes, it is software driven, but at the same time, you know, there's variation in those measurements, and you want to see if you're able to capture those variations. You know, if you do your CMM gauge R&R and you pass, and all of your other features are the same, that's where you can use similarity to say that I can meet, you know, for the same tolerances, I can meet a gauge R&R. But I was surprised the first time I ran one, because a lot of people said, oh, it's, you know, software driven, it's super accurate, but we needed a high accuracy on our parts, and it failed. And so we ended up getting better fixtures and then changing our methodologies for loading the part, and that's how we were able to pass, right? And so that's what you're really looking at, is there's other parts of variation that you need to quantify for a CMM than just the software or the program.
For the 4-to-1 ratio, why are we dividing 0.005 rather than the total tolerance of 0.01?
Yeah, I looked at this morning too, and I thought I was wrong, but it's 0.005 because I also looked at the uncertainty of the gauge. So you can either do total 0.01, but then the uncertainty would have to be doubled as well. So I just did the plus minus on both. So let me go back to that slide. I thought I had it wrong this morning too, and then I realized that you're dividing both. So you divide that by that. So it's a plus minus of that. So if you could do it by the total, but then you would divide it, you know, you would get 0.0025, and so just be the double of that, right? And I think that was the question. So I just divided by that and say if the tolerance given by the supplier for the accuracy, right, if they did an uncertainty ratio in the published literature, typically it's a plus minus. So that's typically how you see it, but you could do it either way. You could do it off of the total, or if you do it off of the half for the plus minus, then it's, you know, the plus minus is listed on the cert given by the gauge manufacturer.
Since a gauge R&R is evaluation of the gauge, how critical is it to use an actual part rather than some kind of standard?
Well, so this debate comes up a lot. What I would say is that the problem with the standard is not the actual part, and I say that because if it looks and behaves like the real part, then I'm better with that, because when you actually have an operator, and this goes especially to manual processes where people are holding parts, he may hold it very different depending on the shape of the part, or he may set it up very different depending on the shape of the part, even on a CMM. So the whole point of that is that we know that the environment plays a big factor, the operator plays a big factor. I don't have it on the slide, but in my opinion, the part itself makes measuring it part of the factors of variation. So if you believe that the part or the facsimile part or some master standard that you have can represent the actual part being measured, then I understand. But if it's not representative of the actual part, in other words, you know, you're measuring, you have to measure a hole on a CMM, but instead of measuring a hole, you're going to just measure the height of a part. I don't know, just as an example. It's not even the same type of feature, then I wouldn't use it. If it is the same type of feature and it looks similar to it and you're going to be measuring it in the same orientation, then that is better. But using the actual part is the best, or something very similar to the part, which in the questions, I believe it does say if you already have this type of part and this type of gauge, right, then, you know, you can probably go straight to doing the gauge R&R. And actually, I've even used a similarity to say that, hey, I've already done this part, right? If it's a tube, it's a tube. I need to measure the diameter of a tube, and it's in the same region. I'm going to use the same gauge and the same tolerance, then you're fine. If it's a completely different part, you know, it's a 1-inch tube, and now I'm measuring a 5-inch diameter tube, I mean, it's going to be a different part. And again, going back to linearity and bias, that you may have issues with linearity too on the gauge. So again, try to use as close as you can to the actual part if you can't use the actual part. But that's probably the best I can tell you, because you will get variation. One other suggestion is if you can always do a correlation to your similar part to the actual part, just to prove that the similar part gives you similar results. In other words, you can almost do like a gauge R&R versus the two parts, and once you prove that they're similar enough, in other words, that they have the same, you know, variation when you measure it, then maybe you can use that for more parts, the master part or whatever you want to call it. Anyway, some suggestions out there, but I always recommend if you can use the actual part, that's the best, because you'd be surprised at the variation you'll see in just from the part.
And Peter, that gives us 1 minute before we end this broadcast, and I just wanted to give you the opportunity to have any final closing comments, and thank you for being a panelist. So if you have any final closing comments.
No, actually, other than thanks everyone for attending. I hope you guys learned something today. This is, again, one of my passions, so hopefully I taught you guys something today, and, you know, holidays are coming up, so I hope everyone has a good holiday.
And I thank everybody for all their questions and attending today and sitting through the whole presentation and hanging around for the Q&A section. So I appreciate that. And what we're going to do is I'll send all the questions that we didn't get to, quite a few more, over to Peter, and we'll see what we can do to improve on the Q&A, where this presentation, the Q&A, along with the webinar, and hopefully this recording will all be posted. So check out the SCMH. After you close out of this, you'll probably be taken to a survey and give it a shot. We'd like to see your input. Thank you, everyone, for attending, and thank you, Peter, for being a panelist today.
Oh, thank you very much, Sue.
Have a great day. Bye.